All right, welcome to the lecture, Lewis dot structures and resonance. You've probably done Lewis dot structures in general chemistry, so hopefully some of this will be a review for you, but the concept of resonance is definitely new to dual chem. So let's take a look and see what's in store. All right, let's first talk about Lewis dot structures in terms of metals bonding with nonmetals. So these are ionic bonds in which a metal atom is going to lose, give up, or transfer, right, his valence electrons to a nonmetal. Okay, and so the metal atom is going to become a positive charge, and the nonmetal atom is going to become a negative charge. And the attraction between the positive ion and the negative ion is going to result in an ionic compound, right? So that's kind of a definition of an ionic compound. So we can show this as Lewis dot structures, where we can show the metal atom with his, for example, sodium, with his one valence electron here, and we can show an arrow there to saying that he's going to transfer it to chlorine. So in the end, when we're doing Lewis dot structures for ionic compounds, we want to make sure that we have our metal atom being a positive charge, right, with no dots around it because he's lost all his valence electrons, and the nonmetal atom gaining the valence electron and becoming a negative charge, right? And so the nonmetal atom will always have 8 valence electrons around him, unless, of course, we are, dealing with like one of the small guys, helium or hydrogen or something like that. So in this case, sodium loses his electron, becomes positive charge. Chlorine gains the electron, becomes a negative charge, and we get that attraction between positive and negative charges, the electrostatic attraction, and it forms the compound sodium chloride. And this is how we would represent it as a Lewis dot structure. So if we're going to do some examples of Lewis dot structures for ionic compounds, let's take a look at these 4. So we'll start with magnesium oxide. So we'll, draw magnesium, and magnesium has 2 valence electrons. All right, so we'll draw 2 dots around magnesium, and he's going to bond to oxygen, who has 6 dots. 1, 2, 3, 4, 5, 6. Okay, and so what's going to happen is, well, you can see that there are 2 blank spots here around oxygen that could be filled with valence electrons, and conveniently magnesium has 2 valence electrons to give or transfer. So those 2 valence electrons are going to go there, and we are going to end up with a Lewis dot structure that looks like this. Magnesium lost his valence electrons. He's a 2+ charge because he had 2 valence electrons, and we'll also have oxygen with a full valence shell, 8 electrons, and because he gained those 2, he's going to be a -2 charge. All right, so that's how we would represent that. Magnesium losing his valence electrons to oxygen, oxygen now having a full octet, becoming a -2 charge, and magnesium becoming a +2 charge. Now, remember, when metals lose their valence electrons, the underneath shell becomes their new valence shell, and that one is always full. So technically, magnesium also has a full valence shell as well. All right, so let's take a look at one other one, and then I'll leave the other 2 for you guys to do. Let's take a look at one that has 2 atoms within a compound. So Na2S. All right, so let's take a look. We've got sodium, and sodium has 1 valence electron. And we're going to hook them up with sulfur that has 6 valence electrons. Okay, so if you take a look at sulfur, he's a nonmetal, so he's going to get electrons, and he's got 2 empty spots to fill. However, sodium only has 1 valence electron. So he only has 1 to give, right, to sulfur. That leaves 1 extra spot there. So that's why it says Na2S. We need 2 sodiums, okay, to come over with their dots to transfer, okay, their valence electrons and give them to sulfur. So he now is a complete octet. So we need 2 sodiums for every 1 sulfur atom. So let's write the final product. We're going to have 2 sodium ions, the positive charge, and we'll have a sulfur with his 8 valence electrons, and he's got a -2 charge. All right, so that's how we're going to represent valence electrons and Lewis dot structures for ionic compounds. Now, in molecular compounds, remember, or covalent compounds, we also call that, electrons are being shared between atoms, right? So not one is strong enough to pull electrons away from the other. So let me just kind of go back and reiterate. In ionic compounds, remember ions or nonmetals have really, really high electronegativity. So they're super strong in pulling electrons towards themselves. So they're going to be able to pull electrons away from weaker elements like metals. Metal atoms have low electronegativity. Remember, they're the ones that have, so many shells, and the valence electrons are like way out there, and it's super hard for them to keep track of them. So metal atoms are going to lose their electrons because they have low electronegativity, and nonmetal atoms are going to gain electrons because they have high electronegativity. Now, in molecular compounds, okay, molecular compounds are covalent compounds, always between 2 or more nonmetals. Remember, nonmetals have high electronegativity values. So they're basically going to be in a tug of war. And so nobody's going to win that fight, and they're going to just kind of concede and share those valence electrons. All right, so that's kind of the reasoning behind molecular compounds sharing those electrons. Now, the shared electrons count towards the octets of both of those atoms. We can see here in water that the valence electrons here for the hydrogens, okay, one of those dots, all right, is being shared with the 6 dots of oxygen, and they count for both towards the octets for both of those atoms. So oxygen now has 8 valence electrons, and for hydrogen to be full, he's not going to have 8, he's the little guy, so he only gets 2 valence electrons, and so you can see that there. All right, now in when we represent Lewis dot structures for molecular or covalent compounds, we're going to have what's called bonding pair electrons and lone pair electrons. So in this case, what we're going to do is, let me just shift it up a little bit. All right, so what we see here is the electrons that are actually between oxygen and hydrogen, those are the bonding pair electrons. And oxygen also has its own electrons in its Lewis dot structure that are already paired up. Okay, and so they are not involved in bonding, and we call those the lone pair of electrons. So the lone pair is non-bonding, okay, and the bonding pair is bonding. All right, so that's the difference between the dots that we'll see in covalent compounds. All right, so if you guys remember back in regular chemistry, you learned about diatomic gases, and most of those diatomic gases were halogens. Remember, diatomic molecules or diatomic gases are always found as like doubles or twins, I call them. So chlorine is not, when chlorine is not bonded to any other element, he's always going to be found as Cl2. Okay, same thing as iodine, I2, bromine, Br2. All of these guys are diatomic molecules or diatomic gases. Well, if we look at the Lewis dot structure of these guys, all of them in the 7th group, the halogens, will all have 1 valence electron in their outer shell. Okay, and so remember that nonmetals have high electronegativity, so they're going to be attracting or wanting to attract electrons from another element or atom. And so if chlorine has one, basically one space available, all right, because there's only one there on that side, it can share, like the chlorine atoms can come together and share their valence electrons super easily to make Cl2, and that's what we see down here, right? So we've got this this valence electron and this valence electron coming together to be shared in the middle there, and we get that diatomic gas. And this is going to work for all the halogens, because remember they all have the same number of valence electrons, so their dot structures are going to look very, very similar. They're just going to have a different symbol in the middle. Instead of chlorine, it'll have a Br for bromine, or maybe an I for iodine. All right, so Lewis dot structures can help us explain why those halogens and why hydrogen as well, right? Because hydrogen has one dot. Well, if you have two hydrogens together, bam, they can share those two dots and make a bond to form those diatomic molecules. Oh, and of course I got ahead of myself, and here is the slide that shows the Lewis dot structure for hydrogen being a diatomic gas as well. So, like I was just saying, hydrogen has one valence electron in its outer shell. It can easily share it with another hydrogen to make a bond there. And now we've got H2, a diatomic gas. All right, so remember the little guys I had mentioned previously? Those guys are not going to make octets. They are only going to make duets, right? Duets means two valence electrons in their outer shell. And these guys are going to be hydrogen, helium, lithium, and beryllium. Those four are smaller atoms, and so they cannot hold 8 valence electrons. If you look at their shell, quantum mechanic, shell structure, remember these guys are, we've got hydrogen and helium only have the one S, right? And lithium and beryllium, they have one S that's filled, and they have two S as well, but they're going to be losing these two valence electrons when they make a bond. All right, so then if you lose those two, all you've got is two left in that valence shell. So these guys are going to be making duets instead of octets. So thus far we've only been talking about single bonds, the sharing of two electrons. However, you can use Lewis dot structures to represent double and triple bonds as well. A double bond is when you have two pairs of electrons being shared. So you've got 4 dots in the middle there. So oxygen, for example, has 2 valence electrons that are unpaired in its valence shell. And so oxygen, and again, another diatomic gas, is going to be able to share those two among the two oxygen atoms to form a double bond. Okay. Now, double bonds are a lot shorter and stronger than single bonds. Okay, so these guys are harder to break than single bonds. So we'll put hard to break. All right, a double bond. Now, triple bonds are even stronger than double bonds. Triple bonds are sharing of 3 electrons in them, or 3 pairs of electrons, I should say, in the middle there. 6 electrons total. And these guys are even shorter and stronger than those double bonds, and so they are super hard to break. In fact, nitrogen, again, another diatomic gas, is the gas that's actually found the most prevalent in our atmosphere. However, when we breathe it in, our bodies can't do nothing with it because it's such a short, strong bond. In fact, the only creatures that can do basically anything and break apart that bond is the nitrogen-fixing bacteria that you may have heard about or remember from biology or AP Bio. Those guys are found in the soil. Those are the only creatures that are able to basically have enzymes that will break apart atmospheric nitrogen in order to use and incorporate them into biomolecules. All right, so to write a Lewis dot structure, there are several steps. And so the first one is to kind of write the correct skeletal structure for the molecule. So to do a skeletal structure, there's a couple of things you need to keep in mind. First, always put the atom that makes the most number of bonds, okay, in the middle. You never want to start with hydrogens or halogens because they can only make one bond. So you want to start with either anything in the carbon group or the oxygen group or the nitrogen group, okay, depending on what compound you're working with. And make sure you put the one that makes the most number of bonds near the center. So if we're doing water, we're not going to do this here with hydrogen in the middle, okay, right? We're going to do, we're going to put oxygen in the middle and then, H's on the sides, okay? So hydrogens and halogens are always at the ends, all right? And remember, lots of molecules are symmetrical. Nature is symmetrical a lot of times, and so molecules are as well. So if, for example, if you've got, oxygen in the middle, it's probably 2 hydrogens on one on either side, okay? So that's the first step. The second step is to add up the total number of valence electrons of each atom in the molecule, and that's how many dots your structure is going to have. So for water, we've got, oxygen has 6 valence electrons, and each hydrogen has 1 valence electron. So 6 plus 1 plus 1 is 8 valence electrons total. So that's how many dots we're going to have in our structure. So it gives you a clue as to how many total dots you'll have in a structure, and that's helpful especially when you get to bigger and bigger molecules. Okay, so once you figured out your skeletal structure and how many dots you're going to have, then you start distributing your electrons among the atoms, giving octets, or remember duets for hydrogen, to as many atoms as possible. So, in the structure for water, you'll put that oxygen, and you'll put, the 8 dots around it, and bam, you're going to have a duet here for hydrogen, the other duet here for hydrogen, and if you look at oxygen, it's got 8 around it, so that's its octet. So you're good to go. Now, if there's any that are missing octets, that's probably means so you put all your dots there and not all of the elements have octets or duets. That means that you're gonna be having either a double or a triple bond. So you want to distribute them as necessary. So for example, if you've got nitrogen, 2 nitrogens, all right. Each nitrogen has 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Right. So that means 5 plus 5 is going to be 10 valence electrons. And so if you're trying to, make dots, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, okay, shoot, we ran out of dots, and this nitrogen over here only has 4 valence electrons total, and that's not an octet, okay, so that is not going to happen. So what you got to think about is you got to do some trial and error and say, well, okay, perhaps it's a double bond. So 1, 2, 3, 4. Okay, 5, 6, 7, 8, 9, 10. That still doesn't work. Okay. Actually 1, because now this guy's got 10 dots, and that doesn't work. But also this guy on the left only has 4 dots. So we want to make sure that we've got equal on both sides and that everybody's got an octet. So perhaps it's a triple bond. So 6, 7, 8, and then 6, 7, 8. Okay, and so that's why nitrogen here, N2, okay, has a triple bond. Yeah, it has a triple bond because he's, this molecule is only going to have 10 valence electrons, and that's how you have to distribute it so that each atom has an octet. All right, so let's try Lewis dot structures for these 2 examples. So CO2. Okay, so again, the first thing you want to do is make a skeletal outline or a skeletal structure of what your molecule is going to look like, and you always start with the one that makes the most number of bonds. So take a look at your periodic table. Is it carbon or oxygen that makes the most number of bonds? Hopefully you said carbon, and so carbon's going to go in the middle, right? and hydrogen and halogens always go last. In this case, we don't have either of those. We've got 2 oxygens. And so remember that a lot of molecules are symmetrical. So we're going to put 1 oxygen on either side. Okay, second step, let's take a look at how many valence electrons we have total. So we've got carbon that has 4 valence electrons, oxygen that has 6, and the other oxygen that has 6. So altogether, we have 16 dots that we're going to do. Okay, so let's start distributing 1, 2, 3, 4, and then maybe we'll do 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, so if we did it like this, the oxygens have octets, okay, but the poor carbon in the middle only has 4 electrons around it. He needs 8. Okay, so nice try. That's not going to work. Okay, so let's try again. So carbon, oxygen, oxygen. So perhaps, okay, so if carbon was 4 short, that means he's got to have 4 extra. So that probably means we're going to have double bonds. So 1, 2, 3, 4, 5, 6, 7, 8. Okay, so now carbon's set. He's got 8, around him in his octet. And then if we do 9, 10, 11, 12, 13, 14, 15, 16. Okay, if we take a look, oxygen has 2, 4, 6, 8. Carbon has 2, 4, 6, 8. And the other oxygen also has 2, 4, 6, 8. Okay, so this is the proper Lewis dot structure for CO2. All right, so we had some trial and error. You have to, you're not going to get it right the first time for all of them. So you're going to have to kind of play with the structures here until you get it right. Okay, so let's take a look at the next one, CCl4, carbon tetrachloride. All right, so again, we're working with carbon or we're working with chlorines. Which one makes the most number of bonds? Hopefully you said carbon. So that's going to go in the middle. And then we've got 4 chlorines. So we've got 4 sides of carbon, and so we're going to put 1 chlorine on each side. Okay, remember we can't have a carbon and then a chlorine and a chlorine, because remember chlorines can only make 1 bond. So that is not going to work. Okay, so let's take a look at how many valence electrons we have total. So carbon has 4 valence electrons, and we've got chlorine that has 7 valence electrons, and we've got 4 chlorines. We have 4 times 7 is 28. 28 plus 4, 32 dots that we're going to be drawing in this Lewis dot structure. So let's get started. 1, 2, 3, 4, 5, 6, 7, 8. Okay, let's do those bonds first because we know we have to make bonds with those dots. 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. Bam. Going to look just like that. Okay, you can also probably know that, in a regular Lewis dot structure, just for the element chlorine, he's going to have 7 dots around him anyways. And so when he makes that bond, that extra dot is going to be right there. So that's another way we know that all the chlorines will have octets all around them. All right, so that's CCl4. All right, so those Lewis dot structures you've probably, have seen before, have done before in regular chemistry. Now we're going to start talking about stuff that we haven't done before in regular chemistry. And the first of it is writing Lewis dot structures for polyatomic ions. Remember, polyatomic ions are groups of atoms with a charge. And they are covalently bonded groups of atoms that have extra or not enough valence electrons. So when you are writing Lewis dot structures for polyatomic ions, you want to pay special attention to the charge of the ion when you calculate your number of electrons. You're going to add, an electron for each negative charge, and then you subtract an electron for each positive charge. Because remember, negative charges mean they have extra electrons, and positive charges means that they have deficient electrons compared to the number of protons. So for example, here's the polyatomic ion cyanate, and if you would add up the valence electrons on the periodic table for both carbon and nitrogen. Carbon has 4 valence electrons and nitrogen has 5 valence electrons. So that would be 9 total, but this polyatomic ion has a negative 1 charge. So you're going to add 1 valence electron for the negative charge. So this structure overall is going to have 10 valence electrons. So when you are writing the Lewis dot structure for it, you want to make sure that you have 10 valence electrons and not 9. And so here you're going to have 6 valence electrons there in the middle, and then here's 7, 8, 9, 10. So the cyanate polyatomic ion looks much like that. Okay, so let's take a look at writing some polyatomic ion, some Lewis dot structures for polyatomic ions. So let's start with NH4. So typically, nitrogen has 5 valence electrons, and hydrogen, right, has 1 valence electron. Okay, but we have 4 of these guys, so overall we're going to have 4. So typically, 5 plus 4 would be 9. However, this is a positive charge, so we are going to subtract 1 electron because it's a positive charge. So that means in our Lewis dot structure, this structure is going to have only 8 valence electrons. All right, so let's remember back to our steps. We're going to figure out which one makes the most number of bonds between nitrogen and hydrogen. That would be nitrogen. Okay, and we've got 4 hydrogens, 1 for each side. And if we said that it's going to have 8 valence electrons, let's do our dots around it, okay, making our bonds. And 2, 4, 6, 8, that's going to be it. And so what we're going to do is we're going to make sure that we put this in parentheses with our +1 charge. Okay, so that is the Lewis dot structure for ammonium. Okay, so let's take a look at a negatively charged polyatomic ion. This one is hydroxide. So again, typically oxygen has 6 valence electrons, hydrogen has 1 valence electron, right? And so if you add those up, that would be 7. However, this is a negative charge, so that means we add an extra electron to it. So this one again is also going to have 8 valence electrons. All right, so OH going to look just like this. All right, and we're going to add the 8 dots. 1, 2 to make a bond. And we remember that hydrogen is one of the little guys that cannot make an octet. So that means all the rest of the dots go around oxygen. And so oxygen has his octet, hydrogen has his duet. They're both happy, and between the two we've got an extra electron, so we have a negative charge. All right, just like in life, there's always exceptions to rules. And so some exceptions to the octet rule. Well, first off, obviously it's impossible to write good Lewis dot structures for molecules that have an odd number of electrons, right? Because one of them will always be unpaired. And then also we need to realize that boron, right here in the periodic table, has only 3 valence electrons, and he forms compounds that only have 6 total valence electrons, not 8. So he's another one of those exceptions. So remember, we had hydrogen and helium and lithium and beryllium, right? And these two guys that made duets. okay, meaning that, they're only going to have 2, dots in their valence shell. Well, when we work with boron, this guy's going to have 6 valence electrons around him rather than 8. Okay, so that's another exception. And then a lot of molecules actually, like SF6 and PCl5, have more than 8 electrons around the central atom. And that's because they have what's called an expanded octet. They can pull electrons from inner shells out to make more bonds, but that is beyond the scope of dual chemistry. That would be AP Chem stuff, and so we don't really go into that. So anything and everything that we'll be doing in this class will not have an expanded octet, and you'll have 8 valence electrons, except obviously if it's one of the exceptions that we talked about. All right, our very last topic for this lecture is resonance. Now, some molecules can have more than one correct Lewis dot structure. For example, here is SO2. Okay, for SO2, there's a double bond in it, okay, but there's just one double bond. You could have the double bond, you could write it on the left side of the molecule. You could also equally write it on the right side of the molecule. Both are correct. Okay, it's just a matter of shifting, the double bond from the left bond to the right bond. Either one works. And so because both are equally correct, we can draw what are called resonance structures. And resonance structures basically just kind of show both correct Lewis dot structures, and they have this double arrow in the middle to kind of represent that in reality, remember the electrons are just wigging out around the nucleus anyways, and so in reality what's happening is that double bond, the electrons are jumping back and forth, making double bond on the left side 1 second, the right side the next second, the left side the 1 second, staying the left side the 1 second, the right side. So in reality, it is an intermediate between these two structures. And so that's what we call a resonance structure. Anytime you've got more than one correct Lewis dot structure for a particular compound, you write all of the possible Lewis dot structures for it, and then write double arrows to represent resonance or an intermediate between those structures. So let's see how that works. All right, so let's take a look and see how it's going to work for a polyatomic ion, nitrate. Okay, so nitrate typically has nitrogen, which has 5 valence electrons, and oxygen, which has 6 valence electrons. And so if we have 3 oxygens, that's going to be 18 electrons, plus the 5, that's 23. And then you notice he's got a -1 charge, so we have to add an extra electron. So that's going to be 24 valence electrons, or 24 dots, that we're going to have in this structure, right? So let's take a look and see how this is going to work. So we know that nitrogen makes 3 bonds and oxygen makes 2. So we're going to start with nitrogen in the middle, and we're going to put our oxygens on either side, right? And we have to have 24 dots. So let's start putting 24 dots. Let's make our bonds. 1, 2, 3, 4, 5, 6. Okay, we'll start doing our octet around oxygen. 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Okay, so on first glance we would say, all right, this looks like legit, except if we take a look at the octet rule, nitrogen is deficient, right? So nitrogen only has 6 valence electrons instead of 8, so that means we're going to have to do double bond. Okay, but we only need 1 double bond, so let's rewrite this with our double bond. Let's just put it there. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so now we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24 dots. All right, so this is legit, but if you notice that there's only one double bond here, right? One double bond. This double bond could go in any of these cases. So when we're doing Lewis dot structures for these, we could have the double bond at the left, the bottom, or the right. Doesn't matter. So that's why we call this a resonance structure, because we could equally draw it like this. We could do nitrogen with the double bond over here, single bond, okay, or we could have this the double bond on the bottom, the single bonds on the outsides, or we could have the double bond on the right instead. Okay, all of these are equally correct, and so all of these are going to be resonance structures of each other. All right, and it's basically going to be an intermediate in between all these, meaning that at any one point it's going to look like any one of these three structures. All right, so that's what resonance is. Equally correct Lewis dot structures for a compound, and we write all of the possibilities there and put arrows in between to say that, hey, look, it's probably a combination of any one of these at one time. Alrighty, so that's Lewis dot structures and resonance, and so you'll be having some practice problems to work on after this, drawing different Lewis dot structures and resonance pieces, and getting lots of practice. All right, we'll see you next time.